So the Snappets is a virtual reality animation system based on projective geometric algebra. Here's an aspiration for you all, a very lofty goal. We want a live programming interface that is so visual that non-programmers can learn something from watching it. So even if you could even have a small child aspirationally looking at you programming. And here's a remark for you all. Brett Victor, I think we all love Brett Victor. And here is Brett Victor's laptop for a while. And if Brett Victor thinks that geometric algebra is a cool enough thing to put on his laptop, then you should probably pay attention to it. That's something that I decided on a while ago. So yes, what can geometric algebra offer visual programming? That's what I want to sell to you all. I'll first show you a recorded demo of Snappets, which was at some point live, I promise. I'll then say why hand gestures are these things called dual quaternions, so they're vitally important if we are thinking about live programming using virtual reality. I'm going to talk about how the geometric product makes code simpler, and I'm going to talk about how geometric algebra allows you to have multiple pictures in the same picture. So first of all, we've got a demo. And introduce everybody to Mr. Alligator. Say hello to Mr. Alligator, everyone. Hey, everyone, nice to meet you. How are you feeling today, Mr. Alligator? Textualize the use of a new technology, otherwise it just seems a bit weird. Well, we don't want you to seem weird, do we, Mr. Alligator? So we're going to contextualize you. You're right. I'm always right, Hamish. And second part of that, where I show you how to make things in Snappets. Now let's say that I want to make an animation of a thing with an eye that can look around. So here's my eye. It's very easy to make. It's just I've got a paint button. So I can add a pupil to that eye. And what we want is to make this eye follow this point around. That'll be a fun thing to see. So how are we going to do that? Well, number one is going to be telling the computer in some sense where the eye is. So I'm going to put that here, and you'll see that I'm doing this sort of Street Fighter Tai Chi hyperloop pose. There's a very good reason for that. All right, so now I'm going to make, this is a So we've got the point where the eye is, we've got the point very far away where the eye is looking, and now I'm going to do this with my hand, and I'm going to press it, and I've made this sort of line, and I'm going to press the button, which makes it so that you can see this flat flashing line here, and now if I let go, we've got a line that is the line that connects that point we made back there with the point that's over here. If I grab that point over there, you see this line moving. All right, let's say that is approximately the quote-unquote tracking this point here. So I'm going to make another line, and here we go. We've now got two lines, and the claim is that the eye should have the pose that takes it from looking in this direction to looking in that direction. So I'm going to grab the eye now. I'm going to turn it in the way that I want it to go. Fairly intuitive thing to do. Now I press my snap button, and it recognizes it's making this line flash and this line flash. And here's the rotation that I want, so I let go, and now we've got the eye following a point. That was freaking difficult. Yeah. Okay, let's make it a bit more sort of cartoony and fun. I'm going to make it a pirate, because that explains why it's only got the one eye. We've got a pirate. I'm going to have some faster tools for making this kind of thing pretty soon. All right, and we're going to have an eye patch. There we go. And we're going to have let's have him have a little tongue sticking out his mouth. He's blowing the raspberry at us. Let's make it so that he's looking at something. So we're going to make a fish. This is my little tribute to Brett Victor, whose idea this significantly is. We've got a fish, and let's have an eye on the fish. That makes it look more cartoony and fun. We've got pupil for it. So here's our fish. We want the pirate to be looking at the fish. So let's make another point with our Street Fighter Hadoken pose. Another point, and this is the point that it's been moved to. And now I grab this point, I press my snap button, and it knows what to do. So now, look, we've got a pirate that is following this fish. It doesn't look great, but it sounds pretty great. Okay, there was Snappets. Now I'll say a little bit about that. So, hand gestures are dual quaternions. What on earth is a dual quaternion? Well, a dual quaternion is a rotation or a translation. Now you see why I needed to ask, needed to berate poor Josh about being on the video. It's a rotation, it's a translation, or it's a screw motion. Every hand motion you've ever made when you pick up a fork or move a mouse or tilt your head or whatever, that is a dual quaternion. Dual quaternions have an axis as well. Here you're seeing me show a purple dual quaternion turned into a rotation and translation part. So it's always a screw motion in general. A rigid motion is another word for this. And dual quaternions are much more visualizable than matrices. That's why you folks, I claim, should pay attention to geometric algebra. The dual quaternion gives you the axis. It's right in there. So, for example, these 3 floats within the 8 floats of a dual quaternion tell you the direction, loosely, that the axis is going in. Whereas getting that same information out of a matrix, well, you can do it, but it's very hard. Okay. Here's another reason that you should care about geometric algebra. So there's this thing called the geometric product in geometric algebra, and it makes it so that you can solve lots of different problems in the same way. Loosely speaking, the geometric product is transform composition, but here's an example of that. So you remember this part of the video. I've set the line of sight for the eye and the line of sight that we want the eye to have, and I've sort of turned the eye using my hand, and we want the program Snappets has given us this yellow rotation here. That rotation is, of course, a dual quaternion, and it so happens that if we call these 2 lines, you know, line start and line end, if you take their geometric product, you get loosely speaking, a transformation from the start towards the end. Okay, it's a tiny bit more complicated than that, but not in a way that I need to get into. And it might sound strange to say we're multiplying 2 lines together, but that's what you do in geometric algebra. You can multiply a plane by a point or a line by a volume. You can do all of that. Here's a more sophisticated usage of the geometric product. So here's 2 video gamey type situations. We've got a shooter where you're defending yourself from a sniper, and you've got somebody who's about to land on some snow on a snowboard. We might want the collision point of this line of sight and this shield that the player has. We might want the place where the snowboard is about to meet the snow. And we might want angles for both, so we're going to turn them both into platonic idealized objects that we're then going to solve problems involving. And it turns out that a thing that's very useful to know about if you're going to solve these problems is a rotoreflection. So what's a rotoreflection? It's very simple. It's just more or less this, right? It's a reflection followed by a rotation. It's somewhere in between a planar reflection and a point reflection. You may or may not have seen a point reflection at any point in your life, but this is a point reflection, and if you imagine, it's defined by the fact that if you move from this fingertip towards this special point, and then out the other end by the same distance, you get to the same fingertip on the other hand. So, planar reflection, point reflection, rotoreflection. It's in between the 2 of them. And a rotoreflection is interestingly defined by both a point, a specific point, and a specific plane. And in geometric algebra, when you can represent a rotoreflection as a matrix, but what we do is we represent it as a point literally added to a plane, which is, again, strange, but that's what we do. but sort of better than a matrix because both things are visualizable. Anyway, so let's try and solve this problem. The way we do it is that we consider a 180-degree turn around that line, followed by a reflection in that plane, and that will give us a rotoreflection. And it so happens that the point of that rotoreflection will be the point where this thing is meeting. The point where this line is meeting this plane defined by the shield. So we've got a rotoreflection defined by these two objects, and it's got a plane in it as well. Maybe we want the angle because we're thinking about, okay, if the bullet deflects off at a certain angle, we want to put a dent or something. And it so happens that you can get this angle by just extracting out this point and this plane part and looking at their sort of amounts, and then taking the arctangent of that ratio. Relatively simple thing to do. A total of 3 lines of code, and we've got some very, very useful information. And that's how you extract the amounts of a point or a plane inside of a rotoreflection. So last part, geometric algebra lets you put multiple pictures in the same picture. And this is something that I think is probably the most important part, but it's the most abstract part. So here's Ken Perlin's Chalk Talk, which is a wonderful visual programming system. It's got multiple spaces, which is a very, very good idea. You want to have this kind of picture, and you want to have relations between the pictures. However, my claim is that there should be as few different spaces as possible if you're thinking about trying to reduce the complexity of something. So to hammer that home, here's a project that I was working on where I started out with 2 spaces, and it was never really satisfactory to me in this situation. And with some iteration, I got it down to 1 space, and I was quite proud of that. And you can play around with this thing there. Here's a link from the previous talk. Comics allow the sort of comic view of the world. Well, comic type explanation. You're going from one picture to another. Perfectly good thing to do. But you don't want to do it unnecessarily. In some sense, you want to put a lot of information onto one picture if you can. That's my claim. And another part of my claim is that vectors. Okay, you all you all know about vectors. Vectors are the thing that we teach to students, and they encourage people to break out things up into lots of different spaces when they don't need to. There's history behind that. You can look up these folks. Anyway, no time to get into that. So a vector can represent a rotation. All right, you can wonder about that rotation. A vector might also be a translation. A vector might also be a point, which is subtly different from a translation. And a vector might be a plane. It might be the normal sticking out of a plane. And all of these different things, I mean, if you had a bunch of vectors and you were trying to solve a problem involving them, you need to know which kind that you're dealing with. And so it's a bit nasty to try to put multiple different kinds of vector into one picture. And so if you apply the sort of Chalk Talk view to this, you end up with a picture like this, which is awful, because these things should be viewed in the same space. All right? That's just the way it should be. And geometric algebra lets you do this because it says a plane is a plane, a point is a point, a rotation is a rotation, a translation is a translation. These are all different kinds of objects, and we deal with them in different ways. Okay, you can kind of turn them into 3 floats if you really need, if you want, for the sake of efficiency, but yeah, it stops you from losing sight of the actual geometric nature of the thing. All right, and if you're interested in this question of multiple pictures in the same picture, or trying to reduce your spaces, so I recommend Brett Victor's Up and Down the Ladder of Abstraction, and I also gave a presentation called Unintuitive Action at a Distance. And if you really like listening to me talk about geometric algebra, here's 2 presentations you can find. 1 second. You just need to type in Hamish Todd GDC into YouTube, and you'll find them. I've actually developed a live programming interface for giving these presentations, which you can play with yourself at this link, but it is very janky, of course. It was mostly designed for those 2 presentations. And so this has been Snappets. You can contact me via these links, and I'm grateful to so many people who have helped me make this work what it is. Yes, I also do fortnightly streams. So thank you all very, very much for listening.